Hello again. Let's continue with virtual memory. In previous chapter, chapter 9, we discussed different memory management strategies used on our computer systems. All these strategies have the same goal, to keep many processes in memory simultaneously to allow multiprogramming. However, they tend to require that an entire process be in memory before it can execute. Virtual memory is a technique that allows the execution of processes that are not completely in memory. One major advantage of this scheme is that programs can be larger than physical memory. So further that, virtual memory abstracts main memory into a large, uniform array of storage. This technique frees programmers from the concerns of memory storage limitations. Virtual memory also allows processes to share files and libraries and to implement shared memory. In addition, it provides an efficient mechanism for process creation. However, virtual memory is not easy to implement and may decrease the performance if it's used carelessly. In this chapter, we try to provide a detailed overview of virtual memory, and we are going to try to examine how it's implemented and try to explore its complexity and benefits. Virtual memory basically involves the separation of logical memory as pursued by developers from physical memory. This separation allows an extremely large virtual memory to be provided for programmers when only a smaller physical memory is available. Virtual memory makes the task of programming much easier because the programmer no longer needs to worry about the amount of physical memory available. She or he can concentrate instead of programming the problem that is to be solved. Here you can see the diagram showing virtual memory that is larger than physical memory. Actually, while discussing the swapping, we discussed a similar model to this virtual memory representation. The virtual address space of a process refers to the logical or virtual view of how a process is stored in memory. Typically, this view is that a process begins at a certain logical address, say the address 0, and exists in contiguously on memory. Although, in fact, physical memory is organized in page frames, and the physical page frames assigned to a process may not be contiguous. We already know that. It is up to memory management unit, your MMU, to map logical pages to physical page frames in your memory. This figure shows virtual address space of a process in memory. So note in that figure that we allow the heap to grow upward in memory as it's used for dynamic memory allocation. Similarly, we allow for the stack to grow downward in memory through successive function calls. Actually, we already discussed the process model, and we know how process is kept in the memory. So this is actually the process model we already discussed in the first chapters. The large blank space or hole here between the heap and stack is part of the virtual address space, but will require actual physical page only if the heap or stack grows. Okay, it's on the logical address space, on the virtual address space, we can reach that addresses, but we only need that parts physically if the heap and stack grows. So virtual address space that include holes are known as sparse address space. Like that. Using a sparse address space is beneficial because the holes can be filled as the stack or heap segments grow, or if we wish to dynamically link libraries during program execution. In addition to separating logical memory from physical memory, virtual memory allows files and memory to be shared by two or more processes through page sharing. You can see the shared library using virtual memory in this figure. So actually, these shared pages, not the physical part of that process or the second process, they are just staying in the memory, on the physical memory. But both processes here, considering virtually that pages, that frames are part of that logical address space for each process. Okay, consider how an executable program might be loaded from secondary storage into memory. One option is to load the entire program in physical memory at program execution time. However, a problem with this approach is that we may not initially need the entire program in memory. An alternative strategy is to load pages only as they are needed. This technique is known as demand paging and is commonly used in virtual memory systems. With demand paging, virtual memory pages are loaded only when they are demanded during the program execution. Pages that are never accessed are never loaded into physical memory. A demand paging system is similar to a paging system with swapping, where processes reside in secondary memory. Demand paging explains one of the primary benefits of virtual memory by loading only the portions of program that are needed. Memory is used more efficiently. We don't need to load all parts of our process. We can just load the page if they are needed, and basically it's called as demand paging. The general concept behind demand paging, as we already mentioned, is to load a page in memory only when it is needed. As a result of that, while a process is executing, some pages will be in memory and some will be in the secondary storage. For that reason, we need some form of hardware support to distinguish between the two. The valid-invalid bit scheme can be used for this purpose. We already discussed the valid-invalid bit scheme while the protection part of the paging. However, this time, when the bit is set to valid, the associated page is both legal and in memory. So it's not just a legal address access right. We are not just checking for the protection. Also, we are considering that if that page is on the memory or not. If the bit is set to invalid, that means the page is not valid. It could be not valid. That's not in the logical address space of the process. Or it's valid, but it's not currently in the secondary storage. Again, you cannot reach that address space. The page table entry for a page that's brought into memory is set as usual, but the page table entry for a page that's not currently in memory is simply marked as invalid. This station is illustrated in this figure. So notice that marking a page invalid will have no effect if the process never attempts to access that page. But what happens if the process tries to access a page that was not brought into memory? So that is the question. That's the problem we have to solve. So access to a page marked invalid causes a page fault. The paging hardware, in translating the address through the page table, will notice that the invalid bit is set, causing a trap to the operating system. This trap is the result of the operating system's failure to bring the desired page into memory. So how we can handle the page fault? The line of action for handling this page fault actually is a straightforward algorithm. First step, we check an internal table, usually kept with the process control block, for this process to determine whether the reference was a valid or invalid memory access. On the second step, if the reference was invalid, we terminate the process. If it was valid, but we have not yet proven to that page, we now page it in. We find a free frame by taking one from the free frame list, for example. That was the third step. And on the fourth step, we schedule a secondary storage operation to read the desired page into the newly allocated frame. On the fifth step, when the storage read is complete, we modify the internal table kept with the process and the page table to indicate that the page is now in memory. And also set the validation bit to valid. On the sixth step, we restart the instruction that was interrupted by the trap. The process can now access the page as it had always been in memory. So here you can see the steps in handling a page fault. Assume that my process needs to access a page, and based on that reference, we are going to check the page table, and we are going to see that page is invalid. So that means we don't have that page actually in our physical memory. So we are going to create a trap. Actually, it's page fault. The page is not on the memory. The page I want to reach is not on the memory. So based on that, I am going to create a trap, and it's called as a page fault. So one of the main jobs of the operating system is to handle the page fault. So the operating system has to handle all traps, but this trap is a special one. It's going to use a mechanism to handle page fault. So first of all, it's going to find the location of the page I wanted, and then it's going to bring that missing piece, that missing page, to the physical memory on a free frame, and then it's going to reset the page table. It's going to write that okay, that page is on that frame, and then this will be a valid one, and then we are going to restart the instruction. So when that instruction is restarted, it's going to find the entry on page table, and based on that page table entry, is going to find the page on the physical memory here. So this is how the operating system handles page faults. In the extreme case, we can start executing a process with no page in memory. When the operating system sets the instruction pointer to the first instruction of the process, which is on a non-memory resident page, the process immediately faults for the page. After this page is brought into memory, the process continues to execute, faulting as necessary until every page that it needs in the memory. At that point, it can execute with no more faults. This scheme is called as pure demand paging. Never bring a page into memory until it's required. Theoretically, some programs could access several new pages of memory with each instruction execution, possibly causing multiple page faults per instruction. This station would result in unacceptable system performance because on every instruction we are going to try to handle more than one page fault. Actually, operating system should handle more than one page fault. So programs tend to have locality of reference, which results in reasonable performance from demand paging. The hardware to support demand paging is the same as the hardware for paging and swapping. So we have page table. This table has the ability to mark an entry invalid through a valid invalid bit or a special value of protection bits. And we need secondary memory. This memory holds those pages that are not present in memory. The secondary memory is usually a high-speed disk or non-volatile memory device. is known as the swap device, and the section of storage used for this purpose is known as swap space. Also, an important requirement for demand paging is the ability to restart any instruction after page fault. Okay, there could be a trap based on page fault, and I'm going to handle that trap. I'm going to handle the page fault. But after that, we need the ability to restart that instruction because, okay, now I have that page on the memory, so you can execute that instruction again. When a page fault occurs, the operating system must bring the desired page from secondary storage into main memory. So actually, that's the theory. To resolve the page faults, most operating systems maintain a free frame list, a pool of free frames for satisfying such requests. So I have to know that if there is a free frame or not, because I'm going to bring some page from secondary storage to memory. So I have to find a free frame to copy that information. So operating systems typically allocate free frames using a technique known as zero fill on demand. Zero fill on demand frames actually zeroed out before being allocated, thus erasing their previous contents. When a system starts up, all available memory is placed on the free frame list. As free frames are requested, for example, through demand paging, the size of the free frame list actually shrinks. At some point, the list either falls to the zero or falls below a certain threshold, at which point it must be repopulated. Demand paging can significantly affect the performance of a computer system. To see why, let's compute the effective access time for a demand paged memory. Assume the memory access time is 10 nanoseconds. As long as we have no page faults, the effective access time will be equal to the memory access time, which is desired as 10 nanoseconds. However, if a page fault occurs, we must first read the relevant page from secondary storage and then access the desired word. To compute the effective access time, we must know how much time is needed to service a page fault. A page fault causes the following sequence to occur. First, trap to operating system, and then on the second step, save the registers and process state. On third step, determine that the interrupt was a page fault. On the fourth step, check that the page reference was legal and determine the location of the page in secondary storage. On the fifth step, issue a read from disk to a free frame. On here, we have A, B, and C steps. On A, wait in a queue until the read request is serviced. On B, wait for the device seek and or latency time on the disk. And at the last step, begin the transfer of the page to a free frame. So these are the first 5 steps. On the sixth step, while waiting, allocate the CPU core to some other processes because actually that process is waiting for an input-output operation. On 7th step, receive an interrupt from the storage I/O subsystem, which is going to message you to I/O is completed. On the next step, on the 8th step, save the registers and process states for the other process if step 6 is executed. And then on the 9th step, determine that the interrupt was from the disk or not, from the secondary storage device. On the 10th step, correct the page table and other tables to show that the desired page is now in memory. And then wait for the CPU to be allocated to this process again. And at the last step, restore the register, process state, and new page table, and then resume the interrupted instruction. So actually, not all of these steps are necessary in every case. For example, we are assuming that in step 6, the CPU is allocated to another process while the I/O occurs. But not all of these steps are necessary. This arrangement allows us multi-programming to maintain CPU utilization, but requires additional time to resume the page fault service routine when the I/O transfer is complete. In any case, there are three major tasks to task components of the page fault service time. First one, service the page fault interrupt. Second one, read the page. Third one, restart the process. So if you are using demand paging on every page fault, instead of just 10 nanoseconds, instead of just accessing the memory, you have to provide that operations. Service the page fault interrupt, read in page from secondary storage and store it on the main memory, and then restart the process to reach that page. So these can be described as the states in demand paging. The operating system could use standard swapping and swap out process, filling all its frames and reducing the level of multiprogramming. However, standard swapping is no longer used by most operating systems due to the overhead of copying entire process between memory and swap space. Most operating systems now combine swapping page with page replacement. Page replacement takes the following approach. If no frame is free, we will find one that is not currently being used and free that frame. We can free a frame by writing its contents to swap space and changing the page table and all other tables to indicate that the page is no longer in memory. We can now use that freed frame to hold the page for which the process faulted. You can see the need for page replacement. Okay, so this is my physical memory, and my physical memory is full. Assume that process 1 wants to reach the page B. Page B is invalid, so that means actually it's not on the physical memory. So a page fault occurred. That means operating system has to page in that page B. But as you can see here, our physical memory is full. So that means we have to select a victim frame and free it. So let's assume that this process is not now using one of that page. So I can replace that page. Let's assume that page out E. So on that case, I have to copy. In this example is 3. I have to copy the page, actually swap out page out to backing store, and I have to set that valid bit as invalid, and then I can move that page to freed frame. Also, I have to update this list. Okay, now B is on, let's say, frame 5. So this is why we need page replacement. And here are the basics of page replacement. We can modify the page fault service routine to include page replacement. Already we discussed the steps of page fault service routine. In this case, we are going to include a page replacement to that routine. On the first step, find the location of the desired page on the secondary storage. Okay. On second step, find a free frame. If there is a free frame, use it. That's not important. If there is no free frame, use a page replacement algorithm to select a victim frame. And then write the victim frame to secondary storage if necessary. And then change the page and frame tables according to that. On the third step, read the desired page into the newly freed frame and change the page and frame tables. And on the last step, continue to process from where the page fault occurred. So notice that if no frames are free, 2 page transfers, one for the page out and one for the page in, are required. This station effectively doubles the page fault service time and increases the effective access time according to that. So we can reduce this overhead by using a modify bit or a dirty bit. When this scheme is used, each page or frame has modify bit associated with in the hardware. The modify bit for a page is set by the hardware whenever any byte in the page is written into, indicating that the page has been modified. When we select a page for replacement, we examine its modify bit. If the bit is set, we know that the page has been modified since it was read reading from secondary storage. In this case, we must write the page to storage. If the modify bit is not set, that means the page has not been modified since we bring it from secondary storage to main memory. So in this case, we need not write the memory page to storage. It's already there. So we can get some time instead of creating a page out mechanism here because it's already on the secondary storage. Okay, we must solve two major problems. Before that, here how we can illustrate a page replacement. Okay, we are going to select the victim. We are going to swap out the victim page if it's necessary, and then we are going to swap in the desired page here, and we have to change the page table in both operations. Okay, as I said, we must solve two major problems to implement demand paging. We must develop a free frame allocation algorithm and a page replacement algorithm. That is, if we have multiple processes in memory, we must decide how many frames to allocate to each process. And when a page replacement is required, we must select the frames that are to be replaced. Designing a proper algorithm to solve these problems is an important task because secondary storage I/O is so expensive. Even slight improvements in demand paging methods yield large gains in system performance. There are many different page replacement algorithms. So we are going to evaluate an algorithm by running it on a particular string of memory references and computing the number of page faults. The string of memory references is called as a reference string. We can generate reference strings artificially, by using a random number generator. For example, we can create a random number generator, and based on that, we can get a string like that. Or we can trace a given system and record the address of each memory reference, and based on that, we can create a string. To determine the number of page faults for a particular reference string and page replacement algorithm, we also need to know the number of page frames available. So we're going to illustrate several page replacement algorithms. In doing so, we use the reference string, this reference string, 701 to 03, and going on. So we are going to use these reference string to test our page replacement algorithms. And also, we are going to assume that we have 3 frames on our memory. So let's start with first in, first out algorithm. The simplest algorithm, the simplest page replacement algorithm is a first in, first out algorithm. A first in, first out replacement algorithm associates with each page the time when the page was brought into memory. When the page must be replaced, the oldest page is chosen. So notice that it's not strictly necessary to record the time when a page is brought. We can create a first in, first out queue to hold all pages in memory. We replace the page at the head of the queue when a page is brought into memory, and we insert it at the tail of the queue. Not tail, of course, tail of the queue. Here, our example. This is our reference string. We have 3 frames. At the initial point, frames are empty. So we need page 7. Page 7 is not on the memory, so that means we have a page fault. Okay, we bring the 7 here. On the next step, our process needs page 0. Page 0 is not on our frames, so I'm going to write it here. It's another page fault. And then we need page 1. Page 1 is not on the memory, that means we have a page fault. So I'm going to bring page 1 here. And then my process needs page 2. Page 2 is not on our memory. We have to bring page 2 to memory, but our frames are full. So we have to choose a victim. Based on the first in first out algorithm, we are going to page out the 7 because it as the first page enters the memory. So we are going to page out it and we are going to write 2 instead of that free frame. On the next step, our process demands page 0. Page 0 is already on the memory, so we don't have a page fault here. So when you have a page fault, you are going to draw that frames and you are going to decide that which page will be removed and which one will be written in based on that. And you are going to find the number of page faults. If you use first in first out algorithm with these reference strings and 3 frames, you are going to get 15 page faults. Okay, so this is how you can apply first in first out algorithm with this reference string to a 3 frame system. To illustrate the problem that are possible with a first in first out page replacement algorithm, consider the following reference strings. Assume that we have a reference string like that. So there will be more page faults in this case. Also, we have another problem here. This figure shows the curve of page faults for this reference string versus the number of available frames. Notice that the number of faults for 4 frames is 10. Here, the page number for 4 frames is 10, which is greater than the number of faults for 3 frames, which is 9. This unexpected result is known as Blaidy's anomaly. For some page replacement algorithms, the page fault rate may increase as the number of allocated frame increases. So we would expect that giving more memory to a process would improve its performance. In some early research, investigators noticed that this assumption was not always true. Blaidy's anomaly was discovered as a result of that. So this is the Blaidy's anomaly on first in first out algorithm. One result of the discovery of Blaidy's anomaly was the search for an optimal page replacement algorithm, because as directly can be seen, first in first out algorithm works, but it's not an optimal algorithm. So we have to find an optimal algorithm. The algorithm that has the lowest page fault rate of all algorithms and will never suffer from the Blaidy's anomaly. Such an algorithm does exist and called as optimal algorithm, or OPT, or opt. It's simply this: replace the page that will not be used for the longest period of time. Use of this page replacement algorithm guarantees the lowest possible page fault rate for a fixed number of frames. So again, I'm assuming that I have the same reference string with 3 frames. On first 3 attempts, I'm going to get page faults, of course. On that point, assume that the process demands the page 2. Page 2 is not on the our frames. So the question is that which page will be my victim? So I'm going to check that the page that will not be used for the longest period of time. Okay, check that one. The 0 will be needed here So I'm going to use 0 on the next axis. And page 1 will be demanded here. And page 7 will be demanded here. So there's a long time to demand of 7. So for that reason, I'm going to replace 7 with 2. Let's check here again. I have 2 for 3 here. So if the process demands 2, it's already here. If it demands 3, it's already here. If it demands 0, okay, it's not on my frame list. So I have to find a free frame for 0. So I'm going to check the next demands. Let's check here. We are here. The 3 will be demanded here and 2 will be demanded here. But the 4 will not be demanded again. So that means, okay, I'm going to replace 4 with 0. So this is how the optimal algorithm works. So as you can see here, we have 9 page faults here. But if you use first in first out algorithm with the same set of string and using 3 frames, we are going to get 15 page faults. For that reason, it's called as optimal algorithm. But unfortunately, the optimal page replacement algorithm is difficult to implement because it requires feature knowledge of reference string. As a result, the optimal algorithm is used mainly for comparison studies. If you want to compare your algorithm, if it's similar to optimal or not, you can use the optimal algorithm. But in reality, you cannot know the reference string as a whole like that. You cannot get the all reference, and based on that, you cannot answer that demands. So you don't have future knowledge on a real system. For that reason, it's just a theoretical approach. We cannot directly use optimal algorithm on our systems. But if the optimal algorithm is not feasible, perhaps an approximation of the optimal algorithm is possible. The key distinction between the first in first out and optimal algorithms, other than looking backward versus the forward in time, is that the first in first out algorithm uses the time when a page was brought into memory, whereas the optimal algorithm uses the time when a page is to be used. If we use the recent past as an approximation of the near future, then we can replace the page that has not been used for the longest period of time. This approach is the least recently used, or LRU algorithm. LRU replacement associates with each page the time that page last use, not last move. When a page must be replaced, this recently used algorithm chooses the page that has not been used for the longest period of time. Let's assume that here we know that the 7 is not used a long period of time, so I'm going to replace 7 with 2. Here, let's check here, we have 0, 3, 2. We are going to add the 1. We know that 0 is the least recently used bit. So I'm going to change the page 0 with page 1. So instead of just checking the time, if you use first in first out algorithm, you are going to just check the time of that page in your memory. But here we are going to just check the least recently used. Okay, here, let's check again. We have 2, 0, and 3. And we want to bring the 4. So we have to choose a victim. 0 is used here. 3 is used here. 0 again used here. And 2 is the least used bit, least used page in this frame. So I'm going to replace 2 with 4. So as you can see, we have 12 faults here. So you can draw that frames for every page fault. Whenever you change the frame, you have to draw that one, and when you count that boxes, you can get the page fault number. In this case, we get 12 faults. It's better than FIFO, which has 15 page faults with this set, but worse than optimal, which has 9 page faults with this set. Okay, so it's not optimal, but it's better than first in, first out algorithm. So the least recently used policy is often used as a page replacement algorithm and is considered to be good. It's a good algorithm. But the major problem is how to implement LRU replacement. An LRU and least recently used replacement algorithm may require substantial hardware assistance. You may need hardware assistance to apply this algorithm. The problem is to determine an order for the frames defined by the time of last use. We have two implementations here, counters and stacks. But before moving that, this part is important. You have to know the page replacement algorithms. You have to understand how you can check on a given reference string and given free frames, how you can check the number of page faults. And in this case, we have first in, first out algorithm, optimal algorithm, and least recently used algorithm. I want you to understand that algorithms, and I want you to actually solve some problems based on that algorithm, how you can decide which one is better than the other one. And I want you to actually compare the difference of the algorithms. Okay, now we are going to continue with the LRU approximation algorithms. Okay, we consider that, okay, LRU is a better option than first in, first out. And we know that we cannot directly implement the optimal algorithm. So we have to find some way to implement LRU. And as I already mentioned, we can use stacks and counters. Actually, not many computer systems provide sufficient hardware support for true least recently used page replacement. In fact, some systems provide no hardware support, and other page replacement algorithms, such as first in, first out algorithm, has to be used on that systems. Many systems provide some help, however, in the form of a reference bit. The reference bit for a page is set by the hardware whenever that page is referenced. Reference bits are associated with each entry in the page table. Initially, all bits are cleared to 0 by the operating system. As a process executes, the bit associated with each page referenced is set to 1 by the hardware again. After some time, we can determine which page have been used and which have not been used, examining the reference bits, although we don't know the order of use. We don't know the order of use, but we can understand that which one is used and which one is not used. This information is the basis for many page replacement algorithms that approximate least recently used algorithm. The number of bits of history included in the shift register can be varied, of course, and is selected depending on hardware available to make the updating as fast as possible. In the extreme case, the number can be reduced to 0, leaving only the reference bit itself. This algorithm is called as the second chance page replacement algorithm. The basic algorithm of second chance replacement is actually first in, first out replacement algorithm. When a page has been selected, however, we inspect its reference bit. If the value is 0, we proceed to replace this page. But if the reference bit is set to 1, we give the page a second chance and move on to select the next first in, first out page. When a page gets a second chance, its reference bit is cleared and its arrival time is reset to the current time. Thus, a page that is given a second chance will not be replaced until all other pages have been replaced or given a second chances. In addition, if a page is used often to keep its reference bit set, it will never be replaced. So it's a good approximation based on that. And here, how we can implement second-chance algorithm. One way to implement the second-chance algorithm actually is sometimes referred to as the clock algorithm, is a circular queue. A pointer, that's a hand on the clock, indicates which page is to be replaced next. When a frame is needed, the pointer advances until it finds a page with a 0 reference bit. As it advances, it clears the reference bits. Once a victim page is found, the page is replaced and the new page is inserted in the circular queue in the position. So notice that in the worst case, when all bits are set, the pointer cycles through the whole queue, giving each page a second chance. It clears all the reference bits before selecting the next page for replacement. So second chance replacement actually degenerates to first in first out replacement if all bits are set. There are many other algorithms that can be used for page replacement. For example, we can keep a counter of the number of references that have been made to each page and develop the following two schemes: the least frequently used and most frequently used algorithms. The least frequently used LFU page replacement algorithm requires that the page with the smallest count be replaced. The most frequently used page replacement algorithm is based on the argument that the page with the smallest count was probably just brought in and has yet to be used. As you might expect, neither MFU nor LFU replacement is common. We cannot use that algorithms commonly because the implementation of these algorithms are very expensive and they do not approximate optimal replacement well. And that's it actually. As I said in this part, the page replacement algorithms are very important. You can consider that this is the most important part of this chapter. You have to be you have to be able to solve page replacement problems using least recently used algorithm, optimal algorithm, and first in first out algorithm on a given reference string with the number of free frames. And that's it for this chapter. We are going to continue with mass storage. I have to give some examples based on the mass storage algorithms, based on the actually finding data on the mass storage on the HDD hard disks. But before that, let's take a break. I'll be here in 10 minutes and then we are going to finish the course and finish the semester with the mass storage.